Hi and welcome back. In the last chapter, we learned what a data engineer is. In this chapter, you'll learn everything about the tools of a data engineer. Let's start with databases. Databases are an essential tool for the data engineer. They can be used to store information. Before zooming into the kinds of databases, let's get some definitions out of the way. According to Merriam-Webster, a database is a usually large collection of data organized especially for rapid search and retrieval. There are a few pieces of vital information in this definition. First, the database holds data. Second, databases organize data. We'll see later that there are differences in the level of organization between database types. Lastly, databases help us quickly retrieve or search for data. The database management system, or DBMS, is usually in charge of this. The main difference between databases and simple storage systems like file systems is the level of organization and the fact that the database management system abstracts away a lot of the complicated data operations like search, replication, and much more. File systems host less such functionality. In the universe of databases, there's a big difference in the level of organization. To understand these differences, we have to make a distinction between structured and unstructured data. On one hand, structured data is coherent to a well-defined structure. Database schemas usually define such structure. An example of structured data is tabular data in a relational database. Unstructured data, on the other hand, is schemaless. It looks a lot more like files. Unstructured data could be something like photographs or videos. Structured and unstructured data define outer boundaries, and there is a whole lot of semi-structured data in between. An example of semi-structured data is JSON data. Another distinction we can make is the one between SQL and NoSQL. Generally speaking, in SQL databases, tables form the data. The database schema defines relations between these tables. We call SQL databases relational. For example, we could create one table for customers and another for orders. The database schema defines the relationships and properties. Typical SQL databases are MySQL and PostgreSQL. On the other hand, NoSQL databases are called non-relational. NoSQL is often associated with unstructured schemaless data. That's a misconception, as there are several types of NoSQL databases, and they are not all unstructured. Two highly used NoSQL database types are key value stores like Redis or document databases like MongoDB. In key value stores, the values are simple. Typical use cases are caching or distributed configuration. Values in document databases are structured or semi-structured objects, for example, a JSON object. For the remainder of this video, let's focus on database schemas. A schema describes the structure and relations of a database. In this slide, you can see a database schema on the left-hand side. It represents the relations shown in the diagram on the right. We see a table called customer and one called order. The column called customer ID connects orders with customers. We call this kind of column a foreign key, as it refers to another table. The SQL statements on the left create the tables of the schema. As you've seen in courses on SQL, you can leverage these foreign keys by joining tables using the join statement. In data warehousing, a schema you'll see often is a star schema. A lot of analytical databases like Redshift have optimizations for these kind of schemas. According to Wikipedia, the star schema consists of one or more fact tables referencing any number of dimension tables. Fact tables contain records that represent things that happened in the world, like orders. Dimension tables hold information on the world itself, like customer names or product prices. Now that you know about databases, let's practice in the exercises. Hi again. Now that you've learned everything about databases, let's talk about parallel computing. In data engineering, you often have to pull data from several sources and join them together, clean them, or aggregate them. In this video, we'll see how this is possible for massive amounts of data. Before we go into the different kinds of tools that exist in the data engineering ecosystem, it's crucial to understand the concept of parallel computing. Parallel computing forms the basis of almost all modern data processing tools. However, why has it become so important in the world of big data? The main reason is memory and processing power, but mostly memory. When big data processing tools perform a processing task, they split it up into several smaller subtasks. The processing tools then distribute these subtasks over several computers. These are usually commodity computers, which means that they are widely available and relatively inexpensive. Individually, all of these computers would take a long time to process the complete task. However, since all of the computers work in parallel on smaller subtasks, the task in its whole is done faster. Let's look at an analogy. Let's say you're running a tailor shop and need to get a batch of 100 shirts finished. Your very best tailor finishes a shirt in 20 minutes. Other tailors typically take 1 hour per shirt. If just one tailor can work at a time, it's obvious you'd have to choose the quickest tailor to finish the job. However, if you can split the batch in 25 shirts each, having 4 mediocre tailors working in parallel is faster. A similar thing happens for big data processing tasks. As you'd expect, the obvious benefit of having multiple processing units is the extra processing power itself. However, there is another and potentially more impactful benefit of parallel computing for big data. Instead of needing to load all of the data in one computer's memory, you can partition the data and load the subsets into memory of different computers. That means the memory footprint per computer is relatively small, and the data can fit in the memory closest to the processor, the RAM. Before you start rewriting all your code to use parallel computing, keep in mind that this also comes at its cost. Splitting a task into subtasks and merging the results of the subtask back into one final result requires some communication between processes. This communication overhead can become a bottleneck if the processing requirements are not substantial or if you have too little processing units. In other words, if you have 2 processing units, a task that takes a few hundred milliseconds might not be worth splitting up. Additionally, due to the overhead, the speed does not increase linearly. This effect is also called parallel slowdown. Let's look into a more practical example. We're starting with a dataset of all Olympic events from 1896 until 2016. From this dataset, you want to get an average age of participants for each year. For this example, let's say you have 4 processing units at your disposal. You decide to distribute the load over all of your processing units. To do so, you need to split the task into smaller subtasks. In this example, the average age calculation for each group of years is a subtask. You can achieve that through group by. Then you distribute all of these subtasks over the 4 processing units. This example illustrates roughly how the first distributed algorithms like Hadoop MapReduce work. The difference being the processing units are distributed over several machines. In code, there are several ways of implementing this. At a low level, we could use the multiprocessing.pool API to distribute work over several cores on the same machine. Let's say we have a function takeMeanAge, which accepts a tuple, the year of the group and the group itself as a data frame. takeMeanAge returns a data frame with 1 observation and 1 column, the mean age of the group. The resulting data frame is indexed by year. We can then take this function and map it over the groups generated by the .groupBy using the .map method of pool. By defining 4 as an argument to pool, the mapping runs in 4 separate processes and thus uses 4 cores. Finally, we can concatenate the results to form the resulting data frame. Several packages offer a layer of abstraction to avoid having to write such low-level code. For example, the Dask framework offers a data frame object, which performs a group by and apply using multiprocessing out of the box. You need to define the number of partitions, for example 4. Dask divides the data frame into 4 parts and performs .mean within each part separately. Because Dask uses lazy evaluation, you need to add .compute to the end of the chain. That was the final example in this video. In the exercises, you'll use the packages yourself. Good luck!